Greetings everybody. This video will hopefully explain how to do online lab number 7, which is deals with conservation of energy involving a mass on a spring. And let me go ahead, and these are just some instructions. Let me go ahead and first bring up the Excel template and get to the simulation. So here's the Excel template. And you're going to be doing the same thing 3 times. You're going to do it once where the spring constant of the spring is relatively small, that's sheet 1. Then you're going to do it for a spring constant that's a medium value, and then for a spring constant that's a large value. And so let me go ahead and bring up the simulation. So here's the link here, masses and springs. And you'll come up with the simulation, and we want to go over here to lab. So I clicked once, I'm going to click again, and it brings up the spring lab. Now notice over here in this box on the right, you want the gravity to be the gravity due to Earth, 9.8 meters per second squared. That's good. Now be careful here with the damping. You want to make sure that the damping is on none, because every time you reset the simulation, it automatically resets the damping to some non-zero value, and we don't want any damping, so make sure you're at none. Okay, gravity 9.8. Now here you want to have click this box that has the displacement and the natural length of the spring. That's the blue line. That is the natural length of the spring, also the equilibrium position. The spring is neither stretched nor compressed. And the displacement, that'll pop up when we start running the lab. You'll see that. Then you also want to click movable line. That's this red line where you can move it. You can move it up and down. I don't think you can move it side to side, but you can move it up and down. Okay, because we're going to use that to read the ruler. And then you got the ruler here. You want to take your ruler and bring it out, and you want the 0 mark of the ruler to be aligned with the equilibrium position of the spring, that blue line right there. So you want the 0 mark of the ruler to be right there. Now remember, in your spreadsheet, you're going to be doing it for a small k value, a medium k value, and a large k value. Well, the only drawback with this simulation is that nowhere does it doesn't give you the k value. It just says here spring constant, small, large. So we're going to have to calculate the spring constant. So that's what we're doing in each sheet. In this section right here for each sheet, notice from cells B8 down over to, well, actually not G but F. But that's what we're doing in this part of each sheet. Before we worry about anything else, we have to get the k value for each spring. And then the same thing for sheet 2. And then the same thing for sheet 3. Okay? You want to get the k value. Notice the k value in each sheet, the k value will be in cell C12. See right there? Right now it says div by 0, which is fine. Okay, so for sheet 1, you're doing the small k value, and I've already got the masses filled in for you. For the other 2 sheets, we'll get to the masses in a minute. Let's worry about sheet 1 right now. And before we get into the whole business with the simulation, basically what we're doing is this. When you stretch a spring from equilibrium, let's call the equilibrium position, that's your initial position of 0. Well, when you add a mass to the spring, it's going to stretch. And so what happens is when you add a mass to the spring stretches. Let me just take 100 and let me put 100 on the spring. And when I let it go, see, it stretches. And now see that green arrow, that's the displacement. That's how much the spring is being compressed relative to its equilibrium position. And you can click slow here. And you can see that green arrow, that's the displacement of the spring from the equilibrium position. Let me go ahead and take the mass off. And so what happens is I'm going to take 100 grams, put it on the spring. Now you want to be careful. See that green arrow? When you release the mass, you want that green arrow to be 0. See right there. That's right there. And then when I let it go, see the spring stretches. And notice it stretches to a maximum length right there. Notice I pause the simulation. When you start it up again, see the mass is going to go back up to the equilibrium position. Then it's going to come back down right there. I'm going to pause it. Now, so what happens is the spring has now stretched the distance. We're calling it XF. Okay. Well, by conservation of energy, the gravitational potential energy of the mass as it moves from equilibrium to XF, because its gravitational potential energy is changing, because it's gone from the equilibrium position to some other position at XF. So its gravitational potential energy has changed. Well, the spring potential energy is also changed, because the spring is now being stretched a distance of XF, which is given by the green arrow. We're going to get that using the movable line in just a second. But let's look at the physics. So what's going on is the gravitational potential energy of the mass, by conservation of energy, must equal the potential energy stored in the spring as it stretches from equilibrium to XF. Well, the gravitational potential energy is simply mg times XF. The spring potential energy is 1/2 k XF squared. Well, before we do the simulation for each of the 3 k values, well, we have to calculate k. Nowhere in the simulation, unfortunately, I don't see anywhere where it gives us a value for k, which is not a big deal. We can calculate it. So and I'll get how to do that in just a minute. So we're getting the k value. And then we know that by conservation of energy, the gravitational potential energy of the mass as it moves from equilibrium to XF must equal the spring potential energy as the spring stretches from equilibrium to XF. So you have PE gravity equals PE spring, or mg XF equals 1/2 k XF squared. Well, initially we need to solve this equation for k. Nothing complicated. K is simply equal to 2 mg XF all over XF squared. Okay, so again, you have gravitational potential energy. Simply doesn't, nothing complicated. The mass is simply, it moves from the equilibrium position. It moves through a height of XF, indicated by the green arrow. So the potential energy is mg XF, just mgh, what we're calling h XF. So mg XF must equal 1/2 k XF squared. Well, first, for each of the cases, small, medium, and large, we need to take this equation and solve for k. Nothing complicated. K is just 2 mg XF over XF squared. Well, what is in the green? What is mg XF? Well, that's just the gravitational potential energy. So k is simply equal to 2 times the gravitational potential energy all over XF squared. So what we're going to do is we're going to enter the formula for the gravitational potential energy, the mg XF. We're going to enter that in cell C11. Then we're going to enter the formula for k in cell C12. So let me go ahead and explain how to do that. And to get the k's, remember, for each spring, we want to get the k values first. So we're going to set for each to get each k value, we're going to use the mass of 100 grams. So I'm going to go back to the simulation, and let me go ahead. So my mass is 100. Again, we don't want any damping. Now, initially, I want a small spring constant, so I'm going to set it down there at the first small setting, right there. Mass is at 100. Okay, I'm going to move it, and now, and notice I want the 0 mark of the ruler to be aligned with the equilibrium position of the spring. I also known as the natural length, that blue line. And then when I hang the mass from the spring, I want to make sure that when I release the mass, I release it from the equilibrium position. So you want to be a little bit careful. And see that green arrow? I want that green arrow to be 0 when I release the mass. See, I don't want to release it, you know, I don't want to release it from there. I don't want to release it from there. I want to make sure that right a little bit, there we go. Oh, yeah, that's good. Okay, so now I have my equilibrium position is the 0 mark of the ruler. Why do I want that? Well, now I can easily measure XF. Now I'm going to hit play, and the mass is going to oscillate up and down. Well, I want XF. I want the maximum distance that the spring stretches. So I'm going to hit play, and there it goes. And notice it's going to stop, and then oscillate back up to the equilibrium position. And then it's just going to keep repeating it. So when it, right there, stop. I'm going to stop the simulation. Then I'm going to go ahead and take the movable line, and I want to set it right at the bottom of that green arrow. You see that? And now, and you can see that, now remember the ruler is in centimeters, but notice right here, my X final, that's the displacement of the spring. Notice it looks like that's 40, it looks like it's 49.5. It's clearly not quite at 50. Looks like right in here, my movable line is at 49.5. And you can, if you're not sure, you can hit play. And it's, you know, it's a little bit tedious, but we can see, you know, how close I am to the, and it looks like perfect. All right. So I know that my XF is 49.5 centimeters. Let me go to my spreadsheet. And now that's right here. We're not worried about anything else. We just want to get the K value. So it's 49.5 centimeters. Well, we want MKS. So over here in cell E9, I need to convert the 49.5 centimeters to meters. So I'm just going to type equals, space, parentheses, space. I like spaces and parentheses to make things easy to read. And I just need to divide cell C9. So I need to do equals C9 divided by 100. I just want to convert centimeters to meters, and then close parentheses and hit check. Oops, got to get it right in. There we go. See, why did it round it? Let me pause this for a second. I don't know why it rounded it to 0.5. Let me try to fix that. Okay, yeah, I fixed it. Let me go back to the simulation real quick. So again, with the movable red line, I know that my X final, again, it starts from equilibrium, hang the mass, the spring stretches to some X final, my movable line. And it clearly is at 49.5 centimeters. That's why we want to set the 0 mark of the ruler equal to the natural length, i.e. the equilibrium position of the spring. So 49.5 centimeters is my XF. So 49.5. Oh, excuse me. My bad. 49.5 right there. Now in cell E9, I just need to convert the 49.5 centimeters to meters. Well, that's just equals space, parentheses, space. I need to do C9 divided by 100 and close parentheses and hit check. There we go, 0.495 meters. Okay, so now the next thing I need to do is remember, we just want to get the K value. I need to enter the formula for the gravitational potential energy. I want that formula, the mgx final, you know, the green. I want that formula, just the green, just the mgx final. I want that to be entered in cell C11. So I'm going to go back. Right here, cell C11. See, PE grab, it's equal to, and then you need equals, space, parentheses, space. Well, my mass is in cell C8. Excuse me. I'm sorry, my mass is in cell E8, right there. That's my mass. So E8, okay, then times, and I might as well do $, because that's not going to change. So I'm going to do $E, $8, okay. Oh, I don't know why. Try that again. So $E, $8. Okay, that's my mass in kilograms. Then G is in cell C5, so I'm going to do times $C, $5. See that? That's mg, then times x final, which is in cell E9. So times $E, $9, and then close parentheses. So that's my mgxf, or mgh, the gravitational potential energy. Hit check. Right there, 0.4851 joules. Okay, that's my PE grav. Now let's go back. Remember, my K is equal to 2 PE gravitational, all divided by xf squared. So I got to enter that formula in cell C12. Okay, so let me go to cell C12, and I need an equals, and then space, parentheses, space. Remember, it's 2 PE grav, all divided by xf squared. So I'm going to do another parenthesis, then 2 times. My PE grav is in cell C11, so 2 times C11. Okay. Close parentheses. Divided by, that's 2 PE grav, divided by xf squared. Well, xf is in cell E9. So divided by, I need 2 parentheses, then E9, close one parenthesis, caret 2, close the second parenthesis, space, last parenthesis. That's just 2 PE grav divided by xf squared. Hit check. And that is my K value, 3.9596. And we'll leave it at that. Okay, that's my K value. Now notice, we're going to use the same mass in sheets 2 and sheets 3. And what you want to do is, again, now notice, remember, all the cell references are, notice all this data here. It goes from cell B5 down to B12, and then from F5 down to F12. Well, notice, same thing. Right there. B5 to B12, then F5 to F. So remember, all you have to do is you just have to take this formula right here, all the formulas, just do copy and do paste, and then go over to sheet 3, do paste, right? Because they're all in the same cell references. Then, so once you type a formula in once, right here, PE grav, cell C11, do copy, and do paste. Obviously, you're getting zeros right now. We don't care. Then do paste. See, that's MGH. Okay, then likewise for your formula for K, you just copy and paste, and don't worry about the div by 0. Paste. So that's all. And so, for example, for sheet 2 with the medium K value, what you'll do is you'll go to I'm going to reset the simulation. Remember, kill the damping, make sure it's 0. You want displacement, movable line. Then, now we want, for the medium K value, I'll go over either of these 2 locations is fine. And then again, we're always starting, and here's our movable line. And again, I want to take my 100 gram mass, put it, I need the ruler. You got to do the ruler. You want the 0 mark of the ruler to be aligned with the equilibrium position. I want to slow. I'm going to take 100 grams, hang it. I want it to be released from the equilibrium position. See that green arrow is not there. Let it go. And then I can see, I'm going to stop it and then get my XF. Move my movable line. And it looks like my XF is now 25. And you can check it. It's a little bit tedious, but it's not bad. And notice my XF is clearly, yep, just go 25. So again, you get the idea. So now I'm on my medium. My XF is 25. And see, notice everything automatically updated. So very simple. So you get, that's how you get the spring constant. Then for large, again, for large, I will go up to right there. And then you might want to take the mass off again. Make sure, then take the mass. Again, when you release it, you don't want any green arrow at all. You want to make sure it's 0. Right there. Oops. Let me try that again. There. And let me see where my XF is. And you can pause it and get my XF. Right there. Okay, let me make sure I've got my XF pretty close. Right. I could go down maybe a smidge, but I think I'm good. Yeah, I could go down maybe a bit. Yeah, it looks like it's 19. Yeah, maybe I could maybe 18. But yeah, it's not gonna matter in 19, 18. But there's my, yeah, looks like 18.5. Yep. Okay, so 18.5. Let me just, that's 18.5. Yeah, 18.5. So again, you go to the spreadsheet. Now I'm on sheet 3. My XF was 18.5. Notice everything updated automatically. That's how you get your K values. Now, so once we do that, now how do we fill out the rest? Well, let me put that in another video. Let me go ahead and save this video and get it posted.